Guys, my name is Ernest and this is Ernest Sciences and the Mathematics TV channel. So our discussion today is going to look at a unique set of representation for a particle in a box. Now in our previous discussions we have been creating emphasis on the concept of a particle in a one-dimension box, which of course we have considered and come up with various ways of representing the degeneracies, or rather the concept of eigenvalues and eigenfunction for various levels. Now in this particular case, we're going to consider a box in a particle in a three-dimension box. And in this case, I'm going to consider perhaps if I give a rough illustration of this specific case, we can have a box being given using that specific representation. I hope it is going to be elaborate in this sense. And we're going to have this one represented as such. So suppose we have a particle in a three-dimension box given in terms of L, X, Ly, and Lz. We are going to consider this specific description of a box using the general representation for this specific case for the energies which we are given in terms of eigenvalues, which is n squared h squared over 8 m l squared given as such. And we have said that we can describe the eigenfunctions using this specific general case for the box in a one-dimension, of course given in terms of, this is the sign of n pi x over l given as such. So this, as we said, represents the eigenvalues and the eigenfunctions respectively. So in this case, if we are going to represent this specific description of a box in a three-dimension or in a three-dimension rectangular box, we're going to represent this in terms of the eigenfunction using this specific wave function representing the values of x, y, and z. And of course, for the energies also, we are going to consider the case of energies which we are going to give in terms of the components of ex, the summation of ex, ey, plus ez, that's specific order. So therefore, this specific discussion is going to concentrate on our ways of representing these specific energies. And of course, as we had said from our first case, we're going to consider the energy outside this specific box to be infinite, and therefore the box is going to be specifically the inside the box is going to be specifically the region whereby this particular electron is going to be contained. So therefore, we're going to consider the Schrodinger's equation, and this is going to be considering the three elements of a space for x, y, and z. Therefore, our general case is going to consist of this specific element for x given as such, and then we're going to have this element for y represented as this, and then the element. So this is the differential operator which we are given, of course, in a one-dimension box using the x coordinates only. So for the z, x, y, and z, we are going to have that full representation, and then this is going to be having 8 pi squared m all over h squared, and then we're going to have E. And we had said that basically this concept of potential energy inside the box is equivalent to 0. So basically we're only going to have the value of E and this wave function, and therefore this is equivalent to 0. So this is the Schrodinger's representation of this specific, of course, particle in this particular case for the particle in a three-dimension box. And therefore we're going to have this specific equations for the of course the energies or the eigenvalues and eigenfunctions represented using this specific characteristic for x, y, and z for the values of n. So suppose we have an eigen function given as the function of n, then therefore this is going to be n in the x-axis, and then we're going to have n in the y-axis, and the wave function of n in the z-axis represented as such, and this is going to give us an overall representation. So we had said that for the value of n, which is for the x, the value for the unknown a represented 2 over l. So therefore we are going to have this one given as the three values for x. So this is for l for x, and then we're going to have 2 over l for y, and then 2 over l for z given as such. And basically that's going to have an implication that if we have a three-dimension box given as such, these are going to appear in terms of 8 over A, or in that case we're going to have 8 over L, and that is going to be the cubed, or 3 times as I've illustrated, and this is going to be the root of that specific representation, and these are going to provide for us the value of A, as we said, from normalizing that specific condition. So this is going to represent the sin over, or the sine over n pi x all over L, and that is for the x, and then we're going to have, so basically this is going to be given as such, and then we're going to have the next for the sine over n pi y over L, and then lastly we're going to have the sine over n pi z over L given as such. So that's the components of this specific eigen function for this specific common, of course, constant, and then we're going to have the components of x, y, and z respectively. So this is going to be the general representation of this specific eigen function for the three-dimension box, and there are various energies, as I said, are going to be given in terms of the components of E, N, X, Ny, Nz, and this is going to be given in terms of perhaps 8ma, and this is going to be a square given as such. So this constant is going to be multiplied by, so the value for this specific element for basically, as we said, is going to be given in terms of L, and this is going to constitute the n value in the x, and this is going to be the square n value in the y and n value in the z component respectively. So these are going to be the summation of these specific energies, and therefore this is going to be the general illustration for the three-dimension box representation for the particle that is existing in that particular case. And of course, as we are going to see, these are going to be the squares of the quantum numbers given in this particular case. And as we are going to see from the description of a particle in three dimension, these are just the respective energies of these specific quantum numbers for x, y, and z. And this implies that we can have a various range of course, this specific unique set of quantum numbers which possess the same energy. And this set of quantum numbers that possess the same energy level are corresponding to independent states of x, y, and z, and they are going to be referred to as degenerate. So in that case, we come across the concept of degeneracies, and therefore these are going to be energies which are going to be given in terms of or different states which are going to be specified by a unique set of these quantum numbers, and of course they are going to possess the same energy at this specific level which I've described in this specific case, and these are going to be given a term that is of course degenerates. And of course, as we go by, we're going to consider several aspects of the representation of various degeneracies of this specific wave function. So catch us in our next video as we're going to look at this various description for these degeneracies and how we can identify them, perhaps, or their various characteristics and applications, especially in different systems of quantum mechanics as we come across them. Now, in this case, of course, I'd like to request our members to check our description boxes for various links of other similar videos that we have put there, which are going to assist us understand this specific concept, since they are going to complement on this particular discussion that we have done. So that is it for now, guys. Bye, God bless you. Catch us in our next video.